center of gravity, and centroid. Good day, everyone. Welcome to Lecture 9, Center of Gravity and Centroid. In this session, we will study how engineers determine the effective location of weight, mass, and geometric centers within objects. These concepts are fundamental in statics because they help us analyze equilibrium, stability, distributed loads, and fluid forces. By the end of this lecture, you will understand the differences between center of gravity, center of mass, and centroid, as well as the methods used to calculate them for various engineering applications.
Concepts defined. We will discuss the concepts of center of gravity, center of mass, and centroid. These concepts are fundamental in statics and engineering because they help us determine where forces effectively act on a body. Understanding these points is essential for analyzing equilibrium, stability, distributed loads, and fluid pressure problems. Throughout this lecture, we will learn definitions, equations, calculation procedures, and practical engineering applications.
Key equations. This slide summarizes the fundamental equations used to determine centers of gravity, centers of mass, and centroids. The center of gravity is calculated based on weight distribution, while the center of mass depends on mass distribution. The centroid is purely geometric and can be determined for lines, areas, and volumes. Notice that all these equations are based on the concept of moments. Essentially, we are finding a point that produces the same moment as the entire distributed quantity. Procedure for finding centroid or center of gravity. To determine a centroid or center of gravity, we follow a systematic procedure. First, select an appropriate coordinate system. Second, define a differential element, such as a small line segment, area, or volume. Third, express the location and size of that element mathematically. Finally, integrate over the entire object using proper limits. This procedure allows us to handle both simple and complex geometries accurately. Centroid properties. Centroids possess several important properties. A centroid always lies along any axis of symmetry. For shapes with multiple symmetry axes, the centroid is located at their intersection. Interestingly, a centroid may lie outside the material itself, as in the case of a hollow ring. For homogeneous materials, the centroid coincides with the center of mass and center of gravity, simplifying many engineering calculations. Composite bodies. For composite bodies, complex shapes are divided into simpler geometric components, whose centroids are already known. We calculate the weighted average of the individual centroids using their masses, areas, or volumes. If the shape contains holes or cutouts, these regions are treated as negative areas, or negative masses. This method is widely used in engineering design because many real structures consist of combined geometric shapes. The theorems of Pappus and Guldinus. The theorems of Pappus and Guldinus provide efficient methods for calculating surface areas and volumes of bodies generated by revolution. The first theorem determines the surface area produced when a curve rotates around an axis. The second theorem calculates the volume generated by rotating an area. These theorems significantly simplify calculations that would otherwise require more complicated integration. Resultant of general distributed load. Distributed loads are commonly encountered in engineering structures. Instead of dealing with infinitely many small load elements, we replace the entire distribution with a single equivalent resultant force. The magnitude of this force equals the area under the load diagram, while its location corresponds to the centroid of that area. This approach greatly simplifies equilibrium and structural analysis. Fluid pressure. Fluid pressure increases with depth, causing a non-uniform pressure distribution on submerged surfaces. The resultant fluid force can be calculated from the pressure distribution and the surface area. An important concept here is the center of pressure, which is the point where the resultant force acts. Unlike the centroid, the center of pressure depends on the pressure distribution and is generally located deeper than the centroid. Application examples. This slide presents practical applications of centroid and center of gravity concepts. Examples include determining the centroid of arcs, parabolas, triangles, and quarter circles. Composite shapes often require the subtraction method when holes are present. Circular geometries are frequently analyzed using polar coordinates. These concepts are also essential in calculating fluid forces on submerged surfaces. Important notes. Several important points should always be remembered. First, look for symmetry because it can dramatically reduce calculation effort. Second, choose the differential element carefully to simplify integration. Third, for composite bodies, standard centroid tables can save significant time. Developing these habits will make solving centroid and center of gravity problems more efficient and accurate.